this, from now we're going to all discuss application. Today I'm going to discuss application of applying HHT for bridge damage detection. Bridge. Everybody has to use bridge. This is a very old bridge. The old bridge does not mean it's not safe or it's not serviceable. Okay, many old bridge. If you go to Europe, you'll find that the bridge near Rome actually has been in use for 2,000 years and it's still being used. Okay, this bridge is Zhaozhou. It's a bridge. It's a graceful arch bridge. It's built in 595 to 605. Yeah, so it's about 1400 years already, and it's still in use. And it's a very graceful bridge. The span, it's moderate. It's not that high, but not that long. But it's respectable, considering it's been built 1400 years ago, and it looks very pretty. And of course, new bridge can also be very graceful. See this bridge goes, it's a curve, it's very nice, and the background is also beautiful. Yeah. So are you a student here? Huh? Oh, you're adjusting system, okay. Because I made a roll call, I don't want to miss anybody. So this is a new bridge. So the moral is that the new bridge can be very pretty and very serviceable, and old bridge can also be beautiful and serviceable. But those bridges are not the norm. See, most of the bridges you cross look like this. Yeah, and it's just old bridge that you build up, look at all the debris. It's not pretty, yeah, but it serves the purpose, yeah. And you look at this bridge. This is a very common bridge that you'll find in Taiwan or anywhere. And the problem is not only it doesn't look pretty, but it has lots of problems. Yeah, look at this bridge. Because of the erosion, the piles start to be exposed. It's all due to the erosion. So a different view looks the same, yeah. And the bridge, a lot of bridge actually collapsed and caused loss of lives. This is one of the bridge that's collapsed in Gaoping Daqiao. It's collapsed in 1989, year 2000. Year 2000, August 28th. Tom, you don't read this. And what this says, Gaoping Daqiao, means this bridge is called the Gaoping Bridge. Suddenly collapsed. Okay. It's so sudden that the car get caught on it. Unfortunately, nobody was hurt. Yeah. This bridge collapsed. I was told that lots of people found the bridge unsafe. They actually called the engineers. They said the bridge is now safe, so the engineering section sent somebody to stand right beside the bridge for about an hour, try to see whether the bridge is or is not safe. But after 1 hour, he get tired. He think, oh, maybe it's all right. He declared the bridge safe, but within an hour, the bridge collapsed. The poor guy lost his job. Yeah. Anyway, so this bridge, the different view is that the previous one said the bridge suddenly collapsed, and this picture says 4 years ago, some European and American expert has already predicted the bridge will collapse. The reason has been that the piles here, the piles has been exposed by erosion, by scouring, and the part that eroded is 4 meters, yeah, already exposed. So the whole bridge, the whole support of the bridge is gone. And this is particularly serious in Taiwan because the construction business try to find sand and gravel for the concrete. So they harvest gravel and sand on the riverbank. Although there's law saying that you cannot harvest the sand and gravel within 500 meters of the bridge, but that doesn't matter because you can harvest way above, way upstream. And once you harvest the sand, then no more sand will flow down, so the riverbed will be eroded. And you can harvest the sand and gravel downstream, but that's also the same, because once you harvest the sand and gravel, then that becomes a sink of sand and gravel. So the sand and gravel will still be washed downstream. By the time for a long time, then this bridge again will be exposed. In Taiwan, I think most of the buildings were built in the last maybe 20 to 30 years. So all the buildings, concrete buildings, the sand and gravel all come from riverbed. And a few constructors try to cut corners. Instead of harvest the sand and gravel from riverbed, they harvest the sand and gravel from beach, and that create more serious problem for the building, because the beach, using sand and gravel from the beach, contains a lot of salt, and the salt made the reinforced bar corroded, and the building becomes really unusable. So so the bridge really did not collapse so suddenly. Yeah, it's 4 years ago people has already said that the bridge has problem, the bridge has problem. And not only that, so you look at this bridge collapsing, and it's all the bridge, whole bridge falling down. And here's a bridge in Portugal. I visited a university and I give this talk, and among the audience was a professor from Portugal. He said, "Oh, we have bridge collapse too." So he sent me these pictures from Portugal. This is a pretty big bridge, and from the newspaper article you can see this bridge is 50 meters, and this part actually collapsed. Yeah. And the original bridge looks like this. Once it collapsed, looks like that. And these are not the most serious collapsing. 2 years ago, there was a bridge in the United States, in Minneapolis. I went to Minneapolis and I still see this bridge still not reconstructed yet. So the bridge has problem. Here is another bridge, which is a relatively new bridge. But fortunately, this bridge is not. This is not even for cars. This is for pedestrians. Yeah, but it collapsed. And this bridge actually was inspected the year before, but it still collapsed. And here's another paper, newspaper article that was sent to me by a professor at Caltech, and he faxed this to me in 2001. And the article said in the United States, 30% of the bridge has deficiency, yeah, structural deficiency. What had happened is that the bridge, most of the bridge in the United States were built in the 50s. That's after Eisenhower. President Eisenhower becomes the president, and he made a decision that he will connect the whole United States by superhighway, by good highway. The reason that he made this decision was that before the Second World War, Eisenhower was a staff member, and he planned an exercise to move one division of troops from New York to San Francisco. This was in the 30s. So when he started this exercise, this whole division troop with all their equipment and everything moving from New York to San Francisco across the United States, the whole trip took 2 months. Yeah, because there's no bridge, no highway. The troop can move from one place to another place and then find there's no more highway available. Then how they're going to move their trucks and how they're going to move their heavy equipment, that becomes a problem. So they have to erect a temporary bridge for the trucks and for the equipment to cross the creeks and rivers and whatever. So after that, he thought that the United States, if the war ever come to the United States, the United States cannot defend itself because it cannot move the troop efficient enough. Then he went to Europe, and he was deeply impressed by the autobahns in Germany. In Germany, Hitler built this superhighway. Yeah, there's no intersection. You just get on there and you drive. To this day, in Germany, there's no speed limit. You get on the highway, you can drive as fast as you want. Yeah. So Eisenhower decided to build this superhighway system. And that's more than 50 years ago, and the bridge started to show aging, show fatigue, wear and tear. So all the bridges that are based on this review, they find that 30% actually has a problem. What if you find a bridge has a problem? There's very little thing that the federal government can do. The bridge safety is actually, the authority is given to local states, and the state inspect the bridge, decide whether the bridge is or is not safe. So out of all this 30% bridge, when they talk about 30% of bridge, they'll talk about the major bridges, not the small little bridge in country road. And those bridges, nobody actually cares. Yeah. So now damage detection is safety monitoring. And in order to avoid this kind of catastrophic accident, so we should have a system to monitor the safety of the bridge, to see whether it has any damage, whether it's still safe to use. And there are 4 levels of damage detection. The first level is to tell people whether this bridge is or is not damaged. Yeah. After you know the damage, then you have to know the location of the damage. First you say the bridge is damaged. The second one is where it is damaged. And third one is the severity of the damage. It's how serious is the damage. Some of the damage may not be serious at all, not related to the structure. So the severity of the damage is important. So if you know the existence, if you know the location, you know the degree or severity of the damage, that tells us a lot. And the last one is the most difficult one. The last one is the life expectancy of the structure. So if I find the bridge is damaged, then you have to know how long can I still use the bridge. Can I use it for another year or another 2 years? Now this is very much a judgment call. This is not something that you can actually look at a bridge and detect. Most of the time, to do this, you need a very sophisticated model to predict the life expectancy of the bridge. So there are 4 levels. If we can do the top 3, I think we have fulfilled our our duty for bridge safety detection. Because the bridge are so important, that millions and millions of cars are passing bridge every day. So the highway department is worried about this safety, so they have spent, in the United States at least, they have spent millions of dollars trying to find the way to detect damage of the bridge. This is what I find out from I work with the Department of Transportation in the United States to find out how they actually inspect the damage, inspect the bridges. The first one is visual inspection. This visual inspection actually is what is being practiced in the United States legally. Each state has a safety inspection team, and the team consists of people in the United States, the people with high school graduation degree. You don't have to have a civil engineering degree, and you can be a bridge inspector. What they do is that you bring those people in and you give them a training. The training is very simple, about a couple months. They give you a list, and the list will say that can I see any rusting on the rails, and can I see any cracks on the bridge surface, can I see any cracks in the supporting structure, and you just look at whatever you can see, and you list those on a form. And once you list that on the form has a rigid criteria to assign points to each question, and those points finally come off the score. The perfect bridge is 10. The bridge is on the verge of collapse is 0. So it's between 0 and 10, then you score. If the bridge score high enough, then the highway department will not bother. They don't worry about that bridge. If the bridge is scored very, very low, then they will send an engineer to look at the bridge. And if they look at the bridge, the engineer thinks that, wow, this bridge is worrisome, the damage is extensive, then the next step is to seal off the bridge and conduct a test. And that test consists of loading. They have a big truck loaded with water or concrete and drive on the bridge. And on the bridge they will use mostly use strain gauge to see how bad the bridge will deform. And based on this test, they will run a model. This model is based on the best guess of the bridge. Why I say best guess? Because most of the bridge, you cannot have a foolproof model. Even if the bridge is new, you have the whole design chart in front of you, you still cannot create a model to fit the bridge. Why? Because most of the bridge that we've seen are concrete bridge, and concrete is very inhomogeneous material. And when you build a bridge, you just specify, I need a very strong, very good concrete, like for example 3,000 psi or 4,000 psi concrete. And when the concrete mixer come up, you can check the concrete. The concrete agree, satisfy your specification, you have to use it. But that concrete can just satisfy barely, or can be way above that. And the strength very much depends upon the construction schedule. Sometimes the schedule is just right, the concrete is mixed just right, and they dump it there and settle perfect. The environmental condition is also good. It's not too hot, it's not too cold, it's not too dry, it's not too wet. So the concrete cures perfectly. Sometimes, the other times, the condition may not be that good. For example, the concrete truck may get caught in the traffic, okay, and the concrete was mixed well, but then you cannot dump it because you haven't get there yet. So the truck will continuously mix this and adding more water. By the time it get there, it's the prime of the concrete is over. Okay, and and maybe the temperature is not right and the humidity is not right. So by the time they're cured, the concrete may still satisfy the specification, but it's not as strong as the another batch. So the bridge, once it's built, it's very inhomogeneous. I remember when I was an undergraduate, I was a civil engineer. I found a summer job in a material test laboratory. Actually, that was right now it's the Gongyan-Yuan. It's what the Gongyan-Yuan Institute of ITRI, Industrial Technology Research Laboratory in Hsinchu. It's the place that now produces a lot of high-tech material. When I was an undergraduate, that was a very sleepy place. It's a little institute, just has concrete and reinforced bar. When I was an undergraduate, that was in the 50s. Taiwan does not make very good steel. A lot of the steel actually was made from the fragment from the guns that fighting in the Jinmen, Kunmen and Mazu, Jinmen and Mazu. Okay, they use the Fei Dan, reclaim that to build the steel, and the steel is very inhomogeneous. Sometimes we get a reinforced bar. We will try to pull and try to pull. It will never break it. Another one, some other time you get a reinforced bar. You put it on. Once you start the machine, it immediately snap. So even the reinforced bar, even the steel may not be uniform. So the bridge is very difficult for you to get a good model. Therefore, using visual inspection and follow that by a model, it's not that reliable, actually. So, however, this was written into law, and all the bridge in the United States has to be inspected every other year. If I inspect this year, next year I do not have to inspect. A year following that you have to do. And the inspection team consists of 2 technicians. They drive a car with a ladder. They go up to a bridge, look around, and then score on the sheets. And that's the way to do it. And now the so-called high-tech inspection is that each one get a handheld calculator or computer. It's like the thing that in the United States you go to read the electricity or gas meter. Once you get there, you punch different numbers into that, and that immediately transmits the data back to your office and automatically score. Then you don't have to worry about the score. But anyway, that's the visual inspection. Even you have a computer handheld evaluator, the basic principle is still the same. Now, in the United States, the highway department spent millions of dollars to develop new techniques. The new techniques is acoustic or ultrasonic. Acoustic is they have sensors. They have sensors put near the bridge, and when the car drives by, they will listen to the popping sound of the structure. Yeah, the popping sound sometimes give you indication of whether the bridge is or is not safe. The other one is ultrasound. Ultrasound has been used for material inspection, especially the very expensive and very precise machinery. They use ultrasound. And you use one ultrasound source and you pick up the ultrasound signal from the other side. I have a very good friend, and he also was my fellow graduate classmate in the graduate school, and he's in ultrasound technology at the United States used to be called the National Bureau of Standards. Now it's called the National Institute of Science and Technology. And he's in the ultrasound group. And he told me that for ultrasound sensor to work, the specimen will have to be as expensive as gold. Okay. In other words, if you want to inspect the bridge is not as expensive as gold by weight, by unit weight. And the bridge structure is so big that you cannot use ultrasound effectively. The ultrasound usually, because ultrasound decay very fast. So you send a signal and receive a signal, they have to be, the source and the receiver has to be very close. So you have to move your sensor and receiver very frequently. And for a bridge, structure like a bridge, it's just impossible. The ultrasound, however, is used very, very often in health. You go to the doctor's office. The doctor's office uses ultrasound lots. A mammogram, you inspect your liver, inspect your heart valves, inspect prostate, inspect all kinds of places use ultrasound. Because the distance, the object that you want to inspect is so small. The structure like a bridge is impractical. And then the next one is using magnetic and electric fields. You generate an electric field, you generate a magnetic field to see how the structure member causes interference. Yeah. Of course, some of the member is more magnetic, send out stronger signal, such as the iron, steel, and the concrete usually do not give you lots of strong signal. So using that, you may be able to detect whether the reinforced bar is or is not good, is intact or not. But this is, again, the area that you look is very small, and also the reinforced bar is buried in the concrete. It's not that easy. It's not that highly precise the way to detect defects. And radiograph is another one that is developed the most for remote sensing. Okay, and most of the radar wave does not penetrate concrete very well. If you want to penetrate concrete, you have to get a huge antenna, so that the wavelength becomes longer, and the longer wavelength has a poor resolution. So that is also a problem. The last one is a thermograph, which is IR, to measure the temperature. Then you will ask, what's the use of measuring temperature of the concrete? The temperature of the concrete sometimes give you some indication. For example, if the concrete has some cracks, the crack will absorb some water, and the water evaporates, and that part will be colder. Okay, so you look at the structure, and you can see certain part it's colder than other parts, and the cold part means that it's wet. The wet means that water has already seeped in, and seeping water is very detrimental to the structure. The reason is that in the severe weather, not here, in severe weather, if you have moisture, the water will freeze and thaw. That will cause the concrete to deteriorate very fast. So all of this method has been developed, but none of that actually give you an indication of safe or not safe. For example, this and all this method will tell you whether there are cracks, and the cracks absorb water. But then the question is that, is crack equivalent to safe or unsafe? It's hard to say. You cannot tell that, yes, I have a crack, therefore the bridge is unsafe, or no, I don't have any crack, therefore my bridge is safe. The cracks and the safety of the bridge is not the same. So finally, there's a new way to actually look at the bridge. They think they can tell the bridge is safe or not, is to look at the vibration, vibratory characteristic. It's just like you try to listen to, you go to a doctor's office and the doctor will tap your body to listen to the sound. This is even more. They try to induce vibration to the structure. And from the vibration, they will try to tell whether the bridge is or is not safe. And the vibration, the characteristic of vibration can be uniquely linked to the stiffness of the member. And so that's why the vibration technique is so important for bridge inspection. And the vibration characteristic actually is related to the what we call the modal analysis. This modal analysis is now a big industry in the United States. Each year they have modal analysis convention, and when you go to that convention, you can see hundreds and thousands of people. Everybody talk about the modal analysis. We'll talk about the modal analysis a little bit details. Yeah. What is modal analysis? Modal analysis actually is looking for the vibration characteristic. They try to look for frequency change. Yeah. So each member has its characteristic of vibration. Yeah. And if the structure becomes damaged or becomes used, fatigue or whatever, the vibration characteristic will change, the frequency will change, the proper frequency will change. By changing the frequency, but the changing frequency is a global signal. It's the whole structure, the signal has to, the frequency has to change. And the sensitivity is very, very low. The other way to do this vibration test is the mode shape changed. Mode shape change is that if, for example, if you play violin, and the violin, the string will vibrate, and if you take a picture, time exposure, you will see the string actually vibrate in all kinds of different ways. Okay, so if you can pick up that vibration, those changing of this vibration, the shape, then you can determine how the string vibrates and what is the proper frequency, and that is more sensitive than total frequency change. But unfortunately, to get the shape change is not that easy. You have to have a detailed definition of each position. Yeah. Suppose I have a bridge which is intact. I'll vibrate it like this. And then suddenly I have a crack, for example. Then I start to vibrate like this. And when I vibrate like this, the whole bridge has a breaking point. We know that when you have a break in the shape, how we can define that, especially the mode. When they say mode, they are talking about the basic Fourier mode of the vibration. So when the structure starts to damage, this mode, you need very high wave number or frequency mode to define a local change. We know that the change in time space or time or space locally means frequency everywhere. That means you have to look at all the high frequency in order to define this change. So this modal location, actually shape change, is again very difficult to get. And the mode shape curvature change, yeah, how the mode change in the curvature in the shape, this is again related to shape. And also the dynamic flexibility. So how flexible is the bridge, is the structure. Yeah. And finally, it's the updating the structural mode parameter. Each structure I have already assigned certain parameters, and as the parameter change, like the stiffness change or the joint changed, the mode will change. So all of this is what they're trying to get from the modal analysis. So as change in mass, change in damping and stiffness, all give the change in frequency, shape, and and the damping characteristic. This analysis or this method is very difficult to implement. I have conducted a literature survey about 3 years ago. I have read thousands papers, not read in detail, scan the papers. I find that most of the paper, successful paper, are all in laboratory. I have not seen any that work in the field yet. The reasons are this. This is number and type of location of the sensor. If you want to define the shape of the bridge, how many sensors do you have to put it in? One sensor? Of course not. One sensor you can only define one point. If you want to define the whole bridge, perhaps you need hundreds. Yeah. But most people don't have hundreds of sensors, because each sensor that it's sensitive for bridge damage detection will have to measure the bridge frequency down to about half hertz. Yeah, vibration to half hertz. And those sensors cost about, at least a few years ago, cost about more than $10,000 a piece. The sensor, and then the data acquisition gears. So it add up, say 10,000. If you have 100, that means $1 million right there just for the sensor. Not many people can invest that kind of money. So the number of sensors to define the mode shape accurately is huge. So many people don't have that many of sensors. They only have maybe 30, which is a large number, and you have implemented 30. Once you put the 30 in, you do not cover the whole bridge. Then what they do is that after the 30 measured half of the bridge, they move to the center part and move to the last part. Okay. They thought that should be good, but it's not going to work. The reason is that the environmental condition is very severe. The bridge, the deformation of the bridge actually depends strongly on temperature. Many bridges, if you measure in the evening and measure in the mid-afternoon, they're totally different. And the signal change from the ambient temperature can be stronger than the damage. So if you have only say 30 sensor, you put in 30 here, you measure in the morning and put the middle section in the noon time and put the other section in the afternoon. You measure 3 different bridges because the temperature is different. Yeah, and this was true when I talked to the group of people at the Los Alamos. The Los Alamos was the place that built the atomic bomb. After they built the atomic bomb, after the war, they don't have anything to do. Of course, they built a few more bombs, but now they don't need that many bombs. The bomb number has already saturated. But now they worry about something else. They worry about how long can they keep the bomb. So you build a bomb. The bomb is in the steel case and sit there. Now how long will the steel case maintain its integrity and not cracking, not leaking, not doing the thing? So they have a special group of people study the bomb casing. Make sure that it's not rusting, it's not cracking, not whatever. So they were very successful, studied the bomb casing. After they finished that, they said, well, gee, what can we do? Then somebody suggested, why don't you look at the bridge if you know how to detect damage? So they went out and tried to detect damage of the bridge. They found all kinds of problems. One of them is the temperature. They were in New Mexico. And New Mexico is a desert. In the evening, the temperature can drop very low, and during the day, the temperature raise extremely high. The fluctuation of the temperature can be more than 20, sometimes 30 degrees during just one day fluctuation. So that is another problem. And not only we need a large number of sensors, but also we need where we put the sensor. Not only where we put the sensor. The low frequency give global information, high frequency give local information. We need high frequency to detect the local damage. But then how you trigger this frequency change? The bridge, if I have a truck drive by, you will sense the vibration. But they cannot tolerate the truck because the truck is random. They want a deterministic shape. So for the modal analysis, they have to trigger the vibration of the bridge by themselves. Now, if you just tap the bridge, it's not effective because the force is too small. The changing of the shape is too small. So what they have to do is they have to shake the bridge strongly. How are they going to shake the bridge strongly without causing extra damage locally? That is another problem. So right now, most of the method is they have the pneumatic hammer, but that is very difficult to employ. So a lot of the case is they have a big truck. They jack the truck up and suddenly release the jack, so that make the truck drop down to the bridge to cause vibration. And it's very difficult to actually conduct the test. Not only that, they also need the information of undamaged state as a reference. You measure the bridge vibration shape. How do you know it's bad? You say, well, when the bridge is new, it looks like this, now it vibrates differently. So you have to have something new or something undamaged as a reference. For bridge, that may not be too difficult because usually a bridge has many different spans. And you can compare this span with other spans. You don't have such a luck that every bridge span all damaged the same to the same degree. So you can usually use the different bridge to different span to make a comparison. But if you do not have that, then you need historical data. Unfortunately, as far as I know, in Taiwan we don't have historical data. Not even in Taiwan, United States, we don't have historical data. Because bridge is built and it's open to traffic and everybody's driving happily across the bridge. Nobody actually take a measurement of the bridge when it's undamaged to make sure that, yeah, I know the bridge, I know the characteristic of the bridge. None. The only exception is in Japan. The Japanese railroad, whenever they build a bridge, before the train get on the railroad, the Japanese made a measurement of the bridge and put in the record. Other than that, I don't know any bridge that has historical record. So whenever you look at a bridge, the bridge is there. That's all you see. Yeah, there's no other information. And another difficulty of the model analysis is stationary and linear assumption. Why stationary and linear assumption? Because when you measure the bridge vibration, you find the bridge vibration, the shape is very different. It's very different. And how can you define that bridge? Then they use Fourier analysis. They say mode 1, mode 2, and different modes. And with the linear, if you use Fourier, you have to make a linear assumption, a stationary assumption to decompose it. But when the bridge is damaged, the vibration can be highly nonlinear. And the damage also causes local change of the mode shape. So it's not that easy for you to actually make that decision. So all of this make a modal analysis difficult to interpret when you actually go out and do it in the field. And so, for example, this is a bridge, and this bridge is supported by that lines. There are some other structures, and if you measure the mode, and this is mode 1, so this is mode 1, and this is mode 2. Mode 2 may be a different mode. Mode 3 may be this, mode 4 may be that, 5 may be this, 6 may be this. You want to define this shape, how many sensors you have to put in to define this shape. It turns out they need 100 sensors per span to define the shape in detail. And this actually comes from the Los Alamos group. Yeah, it's not that easy to define the shape. It's not that easy to actually identify the shape change. So suppose I have a break here, then my deformation will not be smooth, but it will be pointed. And to make that pointed representation, you need a very, very high mode. So this creates a problem for us. We have, in modal analysis, in other analysis, we have an assumption, a list of assumptions. And this assumption is what we think we have. We think that we have a linear system, we have a stationary process, we have a complete database, we have perfect model, yeah, and we have a complete history of the system, yeah. We have unlimited sensor and data, and we are accessible to everywhere. And the bridge, I can put sensor everywhere, yeah. And invariable friendly environment. The data are clean, and we have, this is very difficult. We have a unique damage versus response relationship. Yeah, a damage and a response. What we measure is the response, not the damage. If you have, this is an inverse problem. From the response, you try to define the damage. Yeah. And we have a clear-cut threshold for damage. So you look at the response, you say, aha, this is damage, period. Many times the change are gradual. It's not clear-cut, yeah, and the sensitivity. So it's a slight damage immediately show up. It doesn't work that way. So all of this are the assumptions, and this is what we actually face. We face a non-linear, especially when we have damage. We don't. The process is non-stationary. Most knowledge is incomplete and empirical. Yeah, and a limited number of sensor accessibility is limited. Environment is highly variable. Data full of noise, ambiguous. See, one response can be caused by very different damages, and we have fuzzy boundary. Yeah, and it's insensitive to small damages. So all of these are our problems. And because of that, we have to think of something different. Excuse me, I'll be right back. Sorry. Because of that, I thought of this new approach using HHT. The advantage of HHT is that we don't worry about nonlinearity, and we actually want to use nonlinearity. We don't worry about non-stationary, and we can tolerate a lot of noise in the data, because data mostly high frequency and all that. So what we do is that to detect existence of damage through comparison, we want to compare now versus then. This is most likely impossible because we don't have history. Yeah, and now we are trying to impress the Taiwan high-speed railroad rail system to let us taking some data to detect the damage of the to detect the baseline of the bridge, but we are still negotiating with them. Now we want to compare damaged versus undamaged. That is also difficult for most of the structure. However, for bridge, it is possible because the bridge has many spans. Typically, the spans are identical, so you can compare one span with another span, and usually you can get the comparison. This is the most promising way, is to compare light load with heavy load. Yeah. Why is that important? Because the strength, when you design a structure, typically design a structure in linear regime, the stress and strain follow a linear proportion. Yeah. If the load is light, and it certainly has to be in the linear range. And if you keep adding load until the load becomes very heavy, and sometimes if the structure is still linear, that means the structure is safe. If the heavy load, the relationships start to bend. In other words, they get beyond the linear stage, get to the nonlinear range, then we start to have problem. So the light load versus heavy load is a very important indicator for the health of the bridge. So with that, we can define the existence of the damage and quantify the severity of the bridge. Is even more important. That by using the linear nonlinear criteria. If the response is linear, we say this is safe. If the response is nonlinear, we start to say be careful. If we have a permanent deformation, in other words, even the frequency changed, and that means danger. We have to be careful. So this is a totally new approach for structural damage. How to define nonlinear? We have already covered that. It's by this intrawave frequency modulation. I think we don't have to cover that. See, this is the pendulum, and the nonlinear, instead of harmonics, we're looking for the broadening of the fundamental peak. Why this is better than harmonics? Because harmonics are usually in the higher frequency range, and that usually are the range that where the noise are dominating. So if you have higher harmonics, the higher harmonics will be actually buried by the noise. If you can look at the fundamental frequency and find the fundamental frequency broadening, and that will be a very easily detected and a very sure way to find the problem of the structure. So the damage detection. So overall consideration, we should consider the condition of the structure and environment, and consider limitation on operation. And once we consider that, say where we can put the sensor and how to acquire data. Once you get that, you should consider the data acquisition. data acquisition, you should consider sensor types, what kind of sensor, how many you have, where you want to put it, and you should want a continuous or periodical collection, and what is the data type, digital, what's the length, sampling rate, and considering historic data. And what's the result that you expect? You want to define damage scenario, and you want to define possible variability due to environmental changes, and define the sensitivity and the threshold. And the decision is that you want to find out whether they are indeed the damage, and where is the damage, and how serious is the damage, and how long can I use it. Yeah. And finally is the confidence of your result. So what we find is that if you have the frequency of present frequency with past frequency, with a perfect frequency, there's a ratio. If frequencies start to change, then the structure has sustained permanent damages. Okay, and the ratio of this frequency of the first mode and period of the first mode, these are the passed away of define. What we are doing is that the frequency of damage versus undamaged, just consider the ratio. If the ratio is damaged and undamaged, the ratio is almost near 1, then you don't have to worry. But if ratio is 0.8, then you start to worry. And how to measure this damage? So the case study, we look at the bridge like the picture I shown you. This is the bridge that has piers that is being exposed. And here's the water flow only in this little channel. But when typhoon comes, everywhere is covered with water. Yeah, this is the typical condition in Taiwan. But not only in Taiwan, I was told that even in California, the amount of money they use to maintain the highway, 25% is actually devoted to fight scouring. Yeah, the California River, many of the rivers are also very short because the basin very small in California. It's not like a Mississippi River. Okay, so here the measurement that we made, it's not like the modal analysis. You have lots of sensors put all over the bridge. What we put it here is just one sensor at mid-span. This is a bridge. We put a sensor in the center of the bridge, not in the road center, span center on the side of the bridge. And you let the truck, you let the car passing by. You can see that this is a big truck. The acceleration come to 0.4. This is not physical unit. This is the electric voltage, and plus minus 0.04. And this is a big truck. And you compare this or this. This are still vibration. These are the little cars. It's a sedan, a passenger car. So when the passenger car pass by, the vibration that it created is less than the noise of the big truck. So the big truck causes lots of more vibration than a small sedan, small passenger car or taxi or whatever. So the heavy load and light load, we hope to see they trigger different response. This is the vertical at the span number 1. This is the vertical at the span number 2. Look at this one. This is more than 0.04. Yeah, this is a very heavy truck passing by. And this is a small truck and this little cars passing by. This is span number 2 and span number 3, span number 4. They are all different the sensor for different car passing by, you don't have to close the bridge to traffic. You can just put your sensor there, you can stand on the side. I think most of you perhaps have the opportunity to stand on the bridge when the truck drives by. You will sense the vibration of the bridge under your feet. That's what we measure here. And this is the cross component, the sideways of span number 1, and longitudinal along the bridge. Usually the vibration are not very strong sideways or along the bridge. Along the bridge is only strong if the truck apply the brake. Then that will give longitudinal oscillation. So we use HHT to calculate the Hilbert spectrum. See, yeah. So this is frequency. This is time. Yeah. We see the frequency. Most of the peak around 4 Hertz. That's the basic vibration frequency of the bridge. Yeah. And you can see this was the span number 1. This is span number 2, and this is span number 3. And you see different span react differently. When you look at the side marginal spectrum, what you find here is that for different trucks, for different load, their marginal spectrum are very different. For example, here is 0.002 and 003. What are these? 002 is this one. I'm sorry. This is 002 and 008. 002 and 008 are the heaviest truck. Okay, as compared to other ones like 003 and 009. You see the 003 and 009. 003, 009 is this. It's very benign. 003 is this one. It's very light. Okay, so the response is different between heavy truck and light truck. And what's the difference is that the bridge itself, the frequency is very tight. But however, when you have low frequency, you have a heavy load, the low frequency somehow generates some subharmonics. And this subharmonic is so strong, it's even stronger than the peak. Not only that, even the noise level is already stronger than the little cars. So this bridge, span number 1, definitely has a problem. And this problem is more severe than we thought. Then I know how to explain it. Okay, the subharmonic usually indicate strong harmonic, strong nonlinearity. Without a strong nonlinearity, you will never have subharmonics. We look at the bridge, span number 1. There, in addition to some cracks on the beams, we also see shear failure. That's the bridge put on the bridge put on the abutment. It has already developed some cracks, diagonal 45-degree cracks. Then we look at span number 2. Span number 2. Look at this. Span number 2 is very clean. This is the most clean span. What we have is that we have all this large load, heavy load. The peak of the heavy load and the peak of the light load, they all line up perfectly. There's no subharmonic peaks. Yeah, and if we look at this peak is C11, and the next one C12. Let's look at C11 is the largest load that we have encountered in the measurement. and C12 is also very strong. It means here, but it's bigger than that. C11 has almost 0.05, plus minus 0.5. It's the largest track that we encountered on that particular day. And even under this load, and you compare to the other cars like 14 and whatever, you find that the 14 is this one. The peak is less than the noise level, but the frequency are perfectly aligned. That means this bridge, even under the heaviest load, it behaves still linear. So this span has absolutely no problem. Yeah. But then we look at still another peak, another span. Span number 3. Span number 3, who we look at is 020, this chart number 020. Look at this expansion of the peak. The peak suddenly gets broader. And other than that, 22 and 21, they line up and it's narrow. Only 22 would get a span up. What's 22? 20 is this. 22 is that. Okay? So what we have is for 20 it's spread out. 22 is still okay. So yeah. So 20 is okay. 22 is okay. 20 start to broadening up. So under this load, under the track of this load, the bridge start to get nonlinear. And under that load, the bridge is still okay. So this is the first time we can see how the bridge behaves linearly or nonlinearly. Yeah. So the bridge of span 3, under this load is still okay, but under this load it start to show nonlinear behavior. That is, the stress and strain start to bend, start to become into the plastic range. For this bridge, theoretically or ideally, what we should do is that we should limit the load. If you want a bridge to be safe, you should say, okay, any truck heavier than that, we will not let you get on the bridge. Or you can limit the speed. It says, don't drive too fast. If you drive slow, then the vibration will be smaller. So these are the channels, span 3. We look at the span 4, we have the same thing. Here, only 29 showed broadening. See, 32, 31, 34 still here. Let's look at the 29. See, 29. Whoops, I'm sorry. 29 is this big truck. All the other trucks were fine. Okay, so the heavier truck indeed caused the bridge to broadening. And that broadening of that bridge, based on our analysis, and only on our analysis, show that it's nonlinear behavior. The bridge already, the operation already get into the nonlinear range. This is the first time I have seen anybody talk about nonlinear behavior. You see, this stress, this is strain. Stress strain, if it's linear, that means you can go up and down without any problem. Before the bridge actually collapsed, it has to go through this range. That means you apply more stress and the strain will increase a lot. But it's still not breaking. And by the time you break, you get to this range. Okay? So if we have any method that we can detect that the bridge get into this range, that's the most sensitive. Will the frequency change? No. Yeah. Will the shape change? Yeah, the shape will change. But the shape change is in the degree, not in the geometry. Therefore, I don't think model analysis can pick up this. Okay, so this area is the design range, is the operational range. And once you get to here, then we already have problem. And you can see that for this truck and compare with the other truck, this truck is already unsafe. In Taiwan, many bridges, the load are unsafe because most of the trucks are overloading. It's way beyond the design load. And the most serious overloading trucks are the ones that are hauling sand and gravels. Yeah. They don't want to make many trips. They just load the whole truck and drive by. This is not only true in Taiwan. Last year, I was invited by Zhongshan University. I went to Kangtang to look at some of their bridge, and it's even more scary in the bridge in Kangtang. In Kangtang, north of Guangzhou, it's a little city called Yingde. Yingde produces about, I was told, about 10% of the cement of the whole country, China. See, China uses lots of cement, use over half of the cement produced in the world in building their highway, building their bridges. And Yingde produce 10% of what they use. That's a huge amount. And because if that cement factory closed, the whole GDP of Guangzhou or Kangtang will drop maybe 5% or whatever. So the government says, whatever you do, you cannot interrupt the production of the cement factory. And cement, to produce cement, you need the limestone. Limestone is in the hills, so the cement factory is in the hills. And once they produce the cement, the product will have to be shipped out. And the road was a very small road, and the road was originally a light gauge railroad. But they find the railroad not as flexible as highway, so they tear up the rail and convert to highway. The design load was 40 tons, for 40-ton truck when they designed. I was told the heavy cement truck weighed 200 tons. Yeah, 5 times the design load. And when I went over there are a couple of engineers in charge of the road. Nobody dared to stand under the bridge when they look at the bridge. The bridge is so damaged. I have never seen a bridge like that and it's still being in use. The span, the center of the span cracked. You can see the reinforced bar popped out. Yeah, and that's at the mid-span. The mid-span actually snapped. Another very common thing is that when the bridge rests on the apartment, on the pier, the part that due to shear failure, this part is already crashed. The concrete starts to falling off. Blocks are falling off. And they know the bridge is not safe. They build a superhighway, but the superhighway is a little bit further. You have to drive around the hill. Nobody wants to use it because it's too far and burn more gas. So people still use that small highway. And that small highway, I asked them, why don't you fix it? They said, well, we are fixing it. The way that they fix it is all the bridge that already snapped, they build a steel truss, pop up the bridge temporarily. The popping up part, it's not that rigid. I don't think it will last very long. But the engineer told me, he says, we don't care. We want to use it for 1 more year. Okay? And then they're going to totally rebuilt the bridge and everything, totally rebuilt, widen the road and build a new highway as a special highway for the cement company. Yeah. So I inspect that last year, and so far I haven't heard any truck actually falling off the bridge. Actually, when I took that trip on the airplane to Guangzhou, I looked at the newspaper. There were 2 bridges collapsed on that same day. Yeah, one bridge collapsed exactly like what it is. It's a big old truck sit on the bridge, the whole slab falling off. The truck still on the bridge, but it's in the riverbed. It's not on the bridge. So this is very, very severe, very, very serious business, especially in the developing country, because the overload condition is very serious. In here, if you pull this truck, I forgot what this truck is. Most likely it's the sand and gravel or cement truck. If you stop this, I was told that the policemen, they are not to stop the gravel truck, because those people are well connected. Yeah. So this, however, you can see has already created unsafe condition. That means this stress and strain is already getting to this range. Yeah. So by using this, I believe we have already found a way to detect the bridge safety. Okay. Time is up. We're going to stop here.